Okay, I really hope that's recording.
If not, I get the slides.
That's true. All right. So first things first, please come in if you guys are here for
Just filter
ops.
in. Again,
This
see
is
what.
the sign-in sheet.
Yeah.
Yeah, they're actually already linked in the master sheet also if you guys have that link still.
Yeah.
The sign-in form is also on the master sheet. So like just go to the master sheet, everything is there.
So,
Okay.
yeah, okay.
All right. We already made our introduction. We'll continue. So, before we start our lecture with all like the technical stuff, we're going to do some housekeeping, re-announcing all of our announcements just so that we make sure that we're all on the same page. And then we are also going to reintroduce ourselves. And yeah, so let's get started.
Hey everyone, I'm Eli. I'm the ops co-lead for the year. I'm a second year E major. I love travel and cafes, and I want to learn how to surf. I'm currently rowing. Well, I'm rowing, so.
Close to surfing. I am Miriam. I'm also a second year electrical engineering major. I like doodling and watching video essays while I doodle, and that is my 100% real gaming setup. Please rate it out of 10. Let me know after the lecture.
Alright, so we were actually looking through a lot of you guys' responses to the Google form when you guys replied. And these were some of the terms that came up a lot. A lot of you guys wanted the technical experience. You guys were interested mainly because you wanted projects and technical experience. And the two that came up the most. I know it highlighted engineering a lot, but like this is an electrical engineering club, so I'm not really gonna talk about how engineering, but other than that, you guys are in the right place. We do have all these projects that we're heading to. You'll actually get your first project at the end of lecture today, so be excited for that. It's super simple, don't worry. But we'll get into that here.
Yes. Next slide. The second question that we had in our application was, do you like boba or coffee? And results seem to say that everybody here likes boba. Well, there are some people who prefer coffee, but it's a small minority. There's also some people who like water, which I guess is hydrating, so that's good. Some people like iced apple juice, good for them. But in future competitions, we will make sure to try and get some boba gift cards. So come to the competitions.
Yeah. All right, and then here's our schedule again. You guys don't have to take a screenshot if you don't want to. We have it all linked in the master sheet for these slides. But generally, it's going to be fall. We're going to have 3 lectures in the fall, 2 projects, and 1 workshop. We're going to have, and then in the winter, we're going to have 4 lectures. We're going to have 3 projects and another workshop. And then we're going to end in spring with 3 lectures, 2 projects, and another workshop. So the way this goes, we kind of try to put a workshop every quarter. To kind of even out that system. We also, the capstone project is the majority of spring for you guys, but we wanted to make sure that workshops kind of fell like on the midterm area because that way it's not, you don't have a project and a midterm that week. We know how it is. We did that last year. It was kind of bad, so we don't want you guys to go through the same thing.
All right. Okay, so here are reminders again. We have the lab safety training. I know some of you may be stressed out about that because like it kind of takes forever, but just try and get it done by Saturday. I promise we're putting an early due date for your sake because if you get it done earlier, then you don't have to worry about it later. We also have the deposit. Some people have been coming up to us and asking if they can give us the deposit in cash or in Zelle, and all of that is completely fine. You'll just need to talk to our treasurer, so like let us know if you need that information. But we are going to be going to the lab after this lecture, so you guys can pick up your boxes and also hand in your cash deposits if you have those. Also, we are not a good or service. We are friends, so please pay us as friends, not as goods or services. Thank you. And then if you're done with those, then you can submit the ops contract that needs a screenshot of your deposit or like a picture of yourself with Taylor. And also you need to like check the box that says I did the lab safety stuff. And you are going to need to complete that contract if you want to pick up your box. So we're also going to have a second pickup time for the boxes on Friday. Right now we're planning for 4 p.m. But yeah, and if you need another time to pick that up, then just let us know, like DMS or something, and we can figure something out with you. But we will have more information on that later.
Another reminder is that we have lab hours. Lab hours are 10 to 6, Monday through Friday. They're electrical lab. If you ever need to pick up, talk to us. Just know when our lab hours are. It's up there. You'll see it in the slides. You can take a screen picture if you want later on. We used to have Sparky or a little bot in the Discord chat people. So if you just ask him lab hours at a certain time, it'll tell you. He's kind of been malfunctioning lately, so I don't know if that still works, but we're working on that. I think Webmaster Dom is. And then if you guys ever like in regards to picking up your ops boxes, if you can't pick it up at the first or the second time, just let us know. We'll find an officer to give you the box during the lab hours, whatever time you want, whatever is comfortable for you. We just have to have that ops contract done before you get the box. So
Yes. Okay. And finally, at the end of our lecture, like we've mentioned probably like 3 times already, we are going to have cookies. You guys can socialize, and you will also be able to pick up your ops boxes if you filled out your contract. So that's going to be our day today, I guess. Is there any questions about any of the reminders or any of the logistics, cookies, anything?
no question.
Okay, fantastic.
What kind of cookies?
All kinds. We have chocolate chip. We even have oatmeal raisin. We have double chocolate chip. We have M&M cookies, and I also think sugar cookies.
Oh, yeah.
So, a whole variety pack. Yes.
Where are the lab hours?
So you can find the lab hours. Okay, if you go to the master sheet, you'll get a link to the slides. And if you go to this slide, that lab hours thing in blue, there's a link to the IEEE website, and that's going to have all the lab hours on it. And it's like constantly updated. So you can just check that out if you want to know what our lab hours are.
When in doubt, check the website. We'll follow back up with you if Sparky works. That was so much simpler. You just did like dot hours the first time too. So.
Any other questions? You can also come up to us like at the end of the lecture or something if you don't want to ask right now. Okay, great. Oops, wrong way. All right, we'll begin our lecture.
Alright, so our first lecture is going to be all about circuits. So we're doing circuits in theory and circuits in practice. If you guys know basics about circuits already, this might be a little bit simple for you. Well, that's the premise, but a lot of us need to get a growing stance on it, so just follow with us and then we'll get to the more difficult stuff later on. Maybe you don't have knowledge. Alright, so in terms of circuits in theory, alright, so first off, does anyone who know what voltage is? Can I hear like a raise of hands? Who knows what voltage is? Okay, sweet. So voltage is just that potential difference, which is well, it's the difference in potential energy causing the flow of charge. The way I like to think about it is if you have a water system in, let's say, a house, you have a tank of water and a faucet. Okay, that's the only two things. So the positive terminal of your voltage source would be the tank, and the faucet would be the negative source. So that flow goes from positive to negative. It's measured in volts, and in theory, it's maintained. And so for now, we'll think of it as such. So what that basically means is it's going to be constant. The voltage provided to a circuit is always going to be, let's say if we say it's 3 volts, it's going to stay 3 volts. You won't have to worry about it decreasing over time, which can happen with charging batteries and other issues. And then also, when you're looking at it, already know that red is positive, black is negative. That's important. Also, don't let it touch. That's going to create a whole mess of shorts for you, so you don't want that to happen. Alright, then in terms of current is another aspect of a circuit. If you think about it in that same water analogy, it's the flow of water. So going from that tank to the faucet, it's the water going through the pipe. It's measured in amps. It's represented by I. I don't know why they're two different letters, but that's how it is. It's used by, I think, actually, wait, Ampere's law helps define it, but you guys won't learn that till EC 10. And then conventional current is from that positive terminal to that negative terminal. You normally say that from the battery, when it's connected to the battery, it goes from positive all the way back to to the negative end. If it doesn't connect, it's an open circuit. And actually, electron flow, which is what we discovered much later on, is the opposite way. So you guys probably know that electrons move, not protons, right? So because of that, as much. I'm not like the atom guy, so, but electron flow actually goes the opposite way through the circuit, but we don't really talk about that. We just say conventional because that's how the world has worked for, I think, 80 years before someone discovered that electrons go the other way. And then by then everyone had already made electrons. So, yeah, I think that's it. Okay, and in terms of resistance, a resistor is something that blocks current flow, but it also creates a potential drop across it. A resistor can be identified by a color code, and they also have a kind of like it's either gold or silver, but it identifies the tolerance. In terms of tolerance, it's typically 5, plus or minus 5, 10%, and that helps identify how much leeway there is due to mechanical manufacturing error. So let's say you have like a 100 ohm resistor, it has gold is 10, right?
It says 5%.
5, okay.
Yeah.
Gold is 5. So plus or minus 5%, that means you can have a range of 95 to 105 based on manufacturing. Could be anything in there. That's why we always like to test our equipment before we use it. Usually using a digital multimeter. If you think about it in a water analogy, it's like a hairball clogged in the pipe. So it's like not preventing the current flow completely most of the time. It lets through less water. Oh, it's measured in ohms. And this actually comes down to Ohm's law. So Ohm's law is V is equal to IR, which is voltage is equal to current times resistance. It can be rewritten in those other two ways. This isn't, well, I don't want to say it's a law, so it's always true, but note that for a whole circuit, it means voltage total is equal to current total times resistance total. I remember when I first learned about electronics back in like high school, I took a second to realize that, if you have two resistors, it doesn't mean that it's the same, that you have to add up the resistors first and then to find the current, because that, if you don't know that it's going to be wrong. So note that, and then we're going to actually get into a few problems, I think, on this next slide. All right, so first off, we want you to find the resistance. I actually, if you guys want to take maybe like a minute to try to solve it in your brain, don't get a calculator out. Like, think about it. Sometimes a problem. But in terms of that, we have a 12-volt voltage source and a current of 0.6 amps or 600 milliamps. So what do you think the resistance in the circuit would be? And then if you think you have an answer, raise your hand. Yeah. Yeah, okay, yeah. Wait, is it that? Yeah, no, it is. Yeah, sweet. Okay. We were actually gonna have you come up to do the one on.
We're gonna have you do the top.
Yeah. Okay.
But it's okay. You got the right answer.
My bad. You got the right answer. First try, that's good. And then for example 2, I need someone to come up here and do it on the board if you want to. So raise your hand if you want to. Come on, don't be shy.
I think we have a very
eager
volunteer in the back.
It's between you two. You want to do it? Okay. Okay, come up and do it.
Let's go, volunteer! We'll give you an extra cookie. We'll give you an extra cookie too.
Yeah. Second one, yeah. So first off, we're gonna find the current total. So what's the total current in the circuit?
Okay, well, so these two resistors are in series, so I'm going to sum their resistances together. So the total resistance is equivalent to, definitely not going to have enough room, but 6 ohm resistor 12 volts. So then you can use Ohm's law. 12 volts equals I times R to get R equals 12 volts over 6 ohms, which is 2. Oh, I broke it. Sorry.
No,
No,
it's
it's
fine.
okay.
It's not ours.
Okay.
Yay!
Sorry,
That's
that's
your
good.
answer.
Okay,
Great
alright.
job. Thank you.
Follow-up question. What's the current through the 4 ohm resistor?
The current through the 4 ohm resistor?
Yeah.
Well, it's the same throughout everything. The current?
Yeah.
That's
good.
the right
That's
answer.
Good. So
It's the
if you didn't hear what
same.
he said,
Oh yeah, go for it.
if you didn't hear what he said that the current through the 4 ohm resistor is the same as the current through the 2 ohm resistor. That's true. So again, through that pipe analogy, imagine it's the same pipe going throughout. Oh wait. Yeah.
Yeah.
Okay. So it's the same pipe going throughout. So what that means is that it shares the same water. So if you think about it like that, it's the same water going through everything. So it's the same current going through everything. And it's in series. It's not the same when it's in parallel, but we'll talk about that. I think
Lecture 2, we will talk about resistors in series and in parallel. So if like the adding thing didn't make sense to you, don't worry, we will get to it. It's slightly advanced. Okay. You'll be there very shortly.
Yeah, no worries. Alright, then here we have passive sign connection. So what this basically means is that we consider the power flowing into an element to be positive when it's passive and negative when it flows out. And then the active element is the reciprocal of that, or the dual of that. So out of these, who here thinks that the battery is a passive element? Okay, who here thinks it's an active element? I need to see more hands, bro. I kind of just said it was right. Okay, yeah, you're right. So it is an active element. So what do you think is a passive element in the circuit?
A resistor?
Okay. And then, I guess we didn't go over this symbol for that. By the way, that's an LED symbol, or a diode. It's kind of a diode symbol. It's missing the little arrows. That's the little arrows. It's LED. Like over here on the board, as you might see.
We'll get to that shortly.
We'll get to that shortly. This example is just a bit adequate. So, but also that LED is a passive element in this way.
Okay. Any questions on circuits in theory?
Any questions on the difference between volts and current? Voltage and current? Anyone have that? Yeah.
Quick question on the passive and active.
Yeah.
Is passive stuff just stuff that like parts that require that intake energy or intake electricity, and the active ones that sort of provide electricity? Or
Yeah, for the most part, we kind of, well, for the most part that you'll see here, yes, that's true. In more advanced circuitry, it starts to get a little more confusing.
We don't worry about
But
that.
we'll worry about that when we get to it, and we'll explain it more to you later on. So, any other questions? No? Yes? Maybe? You guys just want to maybe stop talking about it. Okay. So
All right.
now.
My turn. Okay, so now we've learned all about circuits in theory, or at least resistors in theory. And now we're going to talk about circuits in practice. So you might be thinking to yourself, now that we've learned all about resistors, like what's the big point? Resistors are kind of boring. They just sit in a circuit, don't really do much. What can we do to make circuits more interesting now? So I will get into that with the common components that we're going to be using for our future projects, specifically LEDs, which is what you're going to be using in Project 1. Also breadboards, which are very important, and, well, Project 1, spoiler. Okay, so here are the common components that we're going to be using basically throughout the year. So the top 3 are the ones that are probably the most important. That are the battery, the resistor, and the LED. We learned about the resistor. The battery is basically just a voltage source. LEDs, again, we'll get into it soon. The bottom 3 are the push button, which acts like a switch, the capacitor, and integrated circuits. So those are a little bit more complex. Mostly integrated circuits, they can get really complex, but we will get into that in like lecture 3 or something. So just to give you a preview. All right, so now we are on LEDs. So LED, if you didn't know, stands for light emitting diode. You're probably familiar with the light emitting part, but you may not be so familiar with the diode part, so that's what I will be explaining now. So basically, a diode is another type of component that only allows current to flow in one direction, and so we call that component polarized. So there is going to be an anode lead, that's the positive lead, and a cathode lead, the negative lead. And current has to flow from the positive end to the negative end, or else it will never turn on. Another stipulation is that the positive side has to reach a particular voltage, and we call that voltage the forward voltage. And once it reaches that particular voltage, the voltage will be dropped across the LED, and then current will be able to flow through it completely unobstructed. So it's off when the anode is less than the forward voltage, and it's on when the anode is greater than or equal to the forward voltage, and current flows through. However, big however, please pay attention to this. Current has to be limited through the LED or else it is going to burn out. If you don't put a resistor before the LED, then like I said, the current flows completely unobstructed. That is a short circuit, and that is not good because that's going to burn out your LED, and then you can't use the LED anymore, and then you might put it back in the LED drawer, and then somebody else tries to use the LED, and it doesn't turn on, and then everybody's frustrated. So please make sure to calculate the correct value for your resistor. How do you find the right value for the resistor? Well, we will get into that shortly. Okay, so let's test our knowledge a little bit. If we attach our LED to a power source with no resistance, what will happen? I just said this, so hopefully somebody here knows. It will burn out, right? We don't want that to happen, so please don't attach no resistance to it. So how can we use our knowledge of the forward voltage and the forward current to fix this? Does anybody want to give a shot at this? Oh, just number 2. Yes, please.
You add a resistor?
Right, you add a resistor. So we want to make sure that the current going through the LED does not exceed the forward current. If it exceeds the forward current, then that's going to burn it out. So we're going to do a little bit of calculation practice. I think that I'll just actually do this one myself because we'll have future examples. So we have a 9-volt battery. We don't know what a resistor is, but we have a LED with a 2-volt forward voltage and a forward current of 20 milliamps. So we don't want this current to exceed 20 milliamps. And we know that 2 volts is going to be dropped across this LED. So that leaves us with 9 volts minus 2 volts, 7 volts remaining. That's going through, or being dropped across our resistor. So that's what we're going to use to calculate the resistance that we need. So we know E equals IR, right? We're going to say our I is 20 milliamps, and our V is 7 volts. So to figure out what R is, pretty easy. We just do 7 volts divided by 20 milliamps. Does anybody know what this number is?
Wow.
Anybody? Okay, well we know like 7 divided by 2 is 3.5. Okay, yeah. Yes, 350. Very good. Okay, so if you don't know your like place value stuff, don't worry. I'm sure you will have it memorized like me. But milli is like 10 to the negative 3. 10 to the negative 3. So so just like leave that decimal point over here and then do the division. Get 350 ohms. So the smallest resistance that we would want to have here is 350 ohms, so that we're not going to exceed our forward current. But if for some reason, like you don't have exactly 350 ohm resistor, please round up, don't round down. If you round down, then you could burn it out, which is not good, and we don't want that. So also remember that, please. Did this example make sense to everybody? Do you have a question?
Yeah, why did you use 7 volts instead of 9 volts?
Right, so 9 volts, that's the total like battery voltage, right? But then we also have this forward voltage. The forward voltage drops across the LED. Basically that means the LED takes 2 volts in order for it to like turn on, basically. So that's why we don't use it in our calculation for R, because this R is only taking 7 volts.
Okay.
Any other questions? Need to re-explain anything? I'm okay with that too. Yes, please.
So is voltage like just basically split among the components?
Yes, exactly. Yes. Each component is going to have its own voltage drop.
And all of them together adds up to the complete voltage.
Yes, exactly.
And then in terms of what Miriam said about rounding up, a lot of the time I'll get people asking for some resistor, let's say 350 ohms, right? But in the lab, we only have 360 ohms. So it's okay to choose 360 ohms. Just don't choose like the 270 ohm resistor. That's not going to be good for you. So it's always good to round up, or like in terms of what you have available to you, unless it's an absurdly large resistance, choose the one that's next up for that.
The worst thing that's going to happen from rounding up is that your LED is going to be slightly dimmer, which is like, you know, as long as it turns on, who cares? Okay, if we're all good on this, I will move to our next point, which is on breadboards. So you might have seen one before, maybe not, that's okay. Breadboards are basically these little kind of like rectangular plates that have a bunch of holes in them. And we use them in order to prototype circuits, because we can just take a wire and plug it into one of those holes, and all of a sudden we have a magical series of connections that we can make with that one node right there. So if we were to make a cross section of a breadboard, we get this thing right here. You see the little like claws. So you put the wire in, that claw holds on to your wire, and all of a sudden you have all these different connections that you can also make from connection to wire to a different component. Yeah, so this is helpful for prototyping circuits before soldering. If you don't know what soldering is, don't worry, we're not going to be doing much of it. If you want to know what soldering is, go to the soldering workshop that's happening, I think, next week. There's like a sign up form in the Discord if you're interested. But for us, breadboards are usually going to be our final project for all of our projects. Any questions on breadboards? There's also a link there if any of you would like to know more about it. Okay, so now we have a couple more examples. So the first one is going to be another calculation that has to do with LEDs. So see if you guys can try that one. We'll just look at example 1 for now, and let me know if you guys find an answer.
Here's the colors too, if you can't see up there.
Thank you. Does anybody here at least know what the resistance is?
That's totally okay. It takes a second to know.
Yeah, you have to use like the color code chart. Like we don't expect you to memorize it. Just like look up the chart and cross-reference.
But from what I've used throughout time, you'll get used to it more and become like a knack to use to it. Brown is 1. Just so you guys know. So is it okay if I went?
Yeah.
Yeah. Okay. Brown is 1. And black is 0. And I always forget.
2. Yeah.
2. Red is 2. But since it's our third color, it's a multiple, so we do times 10 squared. So can someone tell me what 10 times 1 squared is? What? Say it loud. 100? Okay, sweet. So it's 100 ohms, but what tolerance? To who? You kind of said it earlier. We were discussing it. It's gold. So what does that mean about the tolerance? 5%. Correct.
Very good.
200 ohms, plus or minus 5%. Now use this to apply to the question. Don't worry, you guys won't have to memorize. There's just a really good goal. No one does. Eventually, you like get it in your head. Like you'll remember that purple is 7 because it's the most random color. So I think green is. Oh, yellow's 4. I think green is 6 or 8. You're getting used to it pretty quickly. So.
Anybody have an answer for the current? Anybody confused? We can work through it.
Do you guys want us to do it, or do you guys Let's get consensus. Who wants us to work through it? Raise your hand. Okay. And then who wants to go? I guess we
Alright. So we figured out that our resistor was, is it 100 ohms or is it 1,000 ohms?
Just tenses.
Yeah, but it's like 1000.
Oh, 1,000.
Okay. I think it is 1,000 ohms. That's our resistor.
Yeah.
Okay, and then our voltage is 5 volts. Oh, rip.
You're breaking it.
Yeah. So our voltage is 5 volts, but then we have an LED with a 2 volt forward voltage. So that means we are going to take 2 volts away from our 5 volts because 2 volts will be dropped across our resistor. Or, sorry, across the LED. So minus 2 volts, so we get 3 volts. So we have our voltage, 3 volts, sorry if you can't see. Our resistor is 1K ohms. So to find our current, V equals IR, so I equals V over R. V is 3 volts, R is 1,000. So we end up getting 0.003 amps, or 3 milliamps.
Any questions? Yeah, she got it.
Does this make sense, guys?
Why did you use LED resistance instead of?
So the LED doesn't have a resistance, it has a forward voltage. So the forward voltage is that voltage drop that goes across the LED. So that's the reason why we have to take it away from our source. Does that make sense?
Why did you have? I thought it was 100.
Oh,
Okay, so
that's a multiplication there. It's 1,000.
yeah, so the first one is 1, right? That's like our first digit. The second one is our second digit. And then our last one is like our multiplier. So it's kind of like we multiply. So it's 1, 0 times 10 squared. The red is 2. So we have 10 times 10 squared, which is 1,000.
Any other questions? Yeah.
Can you not Ohm's law on an LED? Like, can you not use Ohm's law on an LED?
Right, so Ohm's law, that only has to do with like resistance, right? LED is a diode, it's not a resistor. It doesn't have resistance. It operates differently. Yeah. So that's the reason why the LED, it just takes the voltage drop. It doesn't have a resistance to it. So we assume that current just flows freely through it.
But okay, but even if we know the current now through the LED and we know the voltage drop of the LED, we can't calculate a resistance of it.
No, because it doesn't have resistance. Right.
Well, this is through experimentation, and you guys are required to know this now, but a resistor works exactly by Ohm's law. So it follows it to a T for LTI circuits. That means that it goes in a straight line. Okay, but for a diode, think about it like it's kind of like an exponential. It does something like this, and there's this little line where it's not on, right? And here is its forward voltage. And that's when it turns on.
So it's not a very low resistance?
Yeah, I guess you could think about it like that, but in
Right.
terms of what we're going to use it for, you just need to know that to solve the current in a circuit, you do this, because the resistance changes. Yeah.
It's kind of like before it reaches the forward voltage, it has infinite resistance. It acts like an open circuit. There's like a break. No current is going through. But once it reaches that forward voltage, it has no resistance. It's just like a wire, and current can pass through freely. Does that make more sense?
Yeah.
Is everybody okay? Are there any more questions? I know this is confusing.
So does the resistance drop the current entire circuit?
Right. The current is completely controlled by the resistor because the LED does not have resistance. You can raise the current by decreasing this resistor. We don't have a diagram, but you can raise the current by decreasing the resistor in series with the LED. That's basically all you can do.
But make sure it doesn't drop below that necessary key resistance, or else you're gonna have a short. Any other questions? Yeah.
Could you also get more current by having like greater voltage?
Yes, that's also true. Sorry. You could also have a greater voltage, and that would give you more current. Thank you.
Any other questions? No? Yeah? No?
So for the resistor, I'm a bit new to this. So for the third one, it's automatically going to be 10 to like the nth power, depending on whatever it is.
Right. Like, so it's 10 to the power of like whatever number that this color indicates. Okay. So like, I would have to look at the thing again, but like if this was black, for example, so black is red, or sorry, black is 0, right? So then that would be like 10 to the 0, and this would just be 10 ohms. If it was brown, black, then it would be 10 times 10 to the 1, so that would be 100 ohms. Does that make sense?
Yeah, I guess the question is kind of like, if the resistor went brown, red, it wouldn't be 11 times 11 squared, right? It would be 11.
No, right, it would be 10 to the power of it, yeah.
Any other questions? Don't be afraid to ask. You all are starting, well, most of you are starting from the same point, but even then, we can all help you out. And some of this can get confusing. You guys actually asked some good questions, like especially in regards to the diet. So, good job, guys.
Please feel free to come up to us at the end if you are confused. Okay, we'll look at example number 2. This one's kind of like a hardware debugging question. It's okay if you're also confused on this one, because it's kind of tricky. Does anybody know why the LED in the second picture doesn't turn on? Well, the first one does. Okay. You've heard from you guys a lot, I'm sorry. Yes.
Because the number one on the right is connected to the negative signal.
Exactly. So I know I didn't really like state this explicitly, but usually we say that the blue side is the ground and the red side is the power. So what's happening here is that the power is not being connected to the power, instead it's being connected to the ground. So there's basically like 0 voltage going through this circuit on this side. Whereas on this side over here, you can see that this one's connected to the red, so there is a voltage like being sent across that circuit. Does that make sense to everybody? Any questions? Okay, you will also be able to experience this when you're making project 1, so feel free to like experiment, as long as you don't blow anything up. And yeah, so this is project 1, the simple LED. We're going to post a spec right after this lecture. So you guys want to look at that. And we're going to have a project 1 work session just like a week from today from 6 to 8 p.m. at the IEEE lab. If you don't know where the IEEE lab is, please follow us after this lecture. We're going to lead you guys there.
You have to follow us anyway to get your ops boxes filled out fast.
Exactly.
Contracts, so.
And it's due the Sunday after the work session, so you have a week and a half to work on it and send us questions and come to the lab and all that stuff.
Oh, and then as a kind of base thing here, if you ever have a question, please either post in ops questions, or if you want to make it kind of secret, DM both Miriam and I in the same chat. That way, if one of us gets to you faster than the other, we know that you got to. But also so that we both see it at the same time. Okay. Yeah.
Is the submission of the project online?
It's going to be a
It's
Google form.
Yeah.
So you'll just have to like take a picture of it, and then there's a couple of check-off questions that you'll have to answer that have to do with like the things you learned in the lecture, basically. Yes.
Will all work sessions be on Wednesdays?
I think this quarter, yeah, just because that was like when we were
I think we have
available.
like 1 on it, or is that workshop?
No, that's the work.
Okay, yeah. Work
Yeah.
sessions are on Wednesdays.
Yeah.
Think about like ops days Wednesday. It's just the one that works best for us. So.
Yeah, and if you can't come in on Wednesdays, there's also like our lab hours, and also like you mentioned, there are a lot of officers who can help with ops. So you can just come whenever the lab is open and
Yes, of course. Please don't limit yourself. We want you to work on it whenever. You can work on it in your dorm room if you want, because you have the ops box. That'll be all of your materials that you need. Any other questions? Yes.
So during the work sessions, we just have access to additional help. There's no difference from going there.
Yeah, pretty much. You might bring snacks too or something, but it'll just be a time where everybody ops is in the same room.
That way you guys can collaborate and also talk to us directly. We'll be there to help you for the 2-hour time. It's also useful because sometimes the lab might be a little bit hectic during lab hours. And though Miriam and I will be there to help you, if you can't make our lab hours, even though I know that a lot of our officers are kind-hearted and would love to help you, sometimes they're also dealing with their own projects and won't be able to help you at that moment. So this is just a good time if you guys have any questions regarding the project to talk to us directly.
Okay. Any other questions?
So when we do a lecture, work session, lecture, work session.
Right, exactly.
Yeah.
Mm-hmm.
Oh, and of course we want you to show up to work sessions, but work sessions aren't mandatory, so don't feel like you have a weekly thing going on here. Lectures, I would say, are mandatory, but of course we have slides on here too, so no worries, guys. If you miss one, then you miss one. Life happens. We aren't going to judge you. Just get that project in and talk to us if you have questions, please. We're always open to asking that. By the way, we had technical difficulties with the email, so I'm so sorry to a lot of you who thought you were declined. That's on, well, I would say that's on me, but that's on the email system. Because apparently we can only shoot out 60 emails an hour. I didn't know this. So, 20 of you guys' emails got trashed, immediately. So I'm really sorry about that. But are you guys getting the emails now? I'm sending it to, a Google group, but, yeah, for the most part? Okay.
Good.
Sweet. So, yeah, sorry about that. And sorry about those of you that, looked at your phone and said, unfortunately. It was a good joke.
A great joke.
Apparently, I was told that it confused a lot of people, so I'm sorry for confusing. But congratulations, we're super happy to work with you guys this year. And if you guys have finished your ops and turned in your ops contract, we're going to go to law right now. So,
thank you all for coming. Okay,